My daughter bought me a Cree headlamp flashlight because she knows that I work on things. I like them because in the past we would use a light that was attached to a cord, and you hang the light near where you wanted to work, and invariably the light would rotate so that it was shining right in your eyes instead of on the work. Whereas with the Cree, if you put it on your head, it shines on the work instead of your eyes. Go figure. Uh, anyway, at some point, there was a piece of metal in the battery compartment of the Cree uh, headlight, and the headlight looks like this, or headlamp. Uh, and that piece of metal eventually worked around to where the chip that turns the light on and off was located, and it shorted out a couple of the terminals, caused a noise. Smoke came out of the unit, and it was destroyed. Well, that chip anyhow was destroyed, and it looks like this. So that's where the chip was. Ignore this. I'll talk about all this later. But the chip was right there, and that board used to be green, but now it's blackened because it got so hot. It got so hot that the chip burned so much I couldn't read the numbers on it. This is a BMS for a battery pack that I got. This is a MOSFET on this circuit board. There used to be one right here, but I took that off and wired that into the light to see if I could get it to work just by happenstance or by chance. This is another circuit board from an electric drill, battery-powered drill. There's a MOSFET right here. There's a power MOSFET back here. And that power MOSFET looks like this. This is the gate, the drain, and the source. Anyway, I tried to wire this into the flashlight to see if I could make it work, but I got varying degrees of results on that too. Anyway, I asked myself at some point in time, why can't I just use a regular transistor to make this work? And that's what I have wired in right here. This is a PNP transistor, and this is the plus side. This goes to the headlamp, and this is the base. So this is the collector, base, and emitter on this transistor. And I got this thing to work. So I'm just going to show you that it does. So you see this little LED right here. That indicates that the light's on. Now it's at lower power. Then it's at flashing. And now it's off. Now the thing about the transistor is that it's never fully off. If you can see that little light, that LED right there that was on when it was on, it's still on just a little bit. So I decided that using that transistor is probably not a good thing, because it'll always be on, even if it's just a little. It will eventually drain the lithium-ion batteries, and draining those kinds of batteries down to zero is not good for them. So I kept looking and looking for the actual chip that would work in this, and about 2 weeks ago I stumbled on a YouTube video that talked about this particular Cree type headlamp flashlight, and the fellow that was running it, and that is in the playlist at the bottom of my video here, if you want to take a look at that. he said what that chip number was, and when I went online to find it, I found it, ordered it, and that's what I'm going to wire in next to see how that works. I wired the chip into the circuit. Now, I didn't put it on the circuit board. I wired it up to these pigtail wires so that I wasn't constantly soldering on the circuit board and making it even harder to install permanently. But let's go see if it's going to work. So there's the high side. There's medium, there's the flash, and there's off. And I'm going to turn it back on again, so I'm thrilled about this. It's off scale. It's just under an amp that it draws. On the lower setting, it's, let's see, 500 milliamps. Here's the 500 scale, or 50 scale, 500. And that's what we're on right here, 500. Milliamps, and it's at the 10, so that means it's at 100 milliamps. And flashing, it's about 260 milliamps. And when it's off, it's really off. You can see that little LED in there is not even a hint of it being on. I made this circuit diagram for this headlamp flashlight so that I could, better visualize what was going on. This is the controlling chip here. It's a CX2812, and that was still visible on the device, the chip. I'm not an electrical engineer or an electronics expert, but I guess this kind of shows that even somebody that's not a professional at it can muddle their way through a fix on something if you have enough determination. Anyhow, from that video I mentioned earlier, I got this number, 9435, and that's the chip that you saw working the flashlight just a minute ago. This is the gate of this MOSFET, and it's a P-channel MOSFET, P-channel, and this is a high side switch. Most of the time, or many times, more often than otherwise, more often than what this is, these chips connect to ground to turn something on, whereas this connects the positive to the light, and then the current goes through the light to ground. So this is the battery plus. It comes over here to the source of this P-channel MOSFET. This gate through this 10,000 ohm resistor, this gate turns on, and current goes through the chip to the drain, from the source to the drain, through this lead and out to the flashlight. This is the key. When you press the button on the headlamp part, the key indexes this chip through the various functions of the flashlight. This is the 9435 chip. I've got my meter set at checking for continuity, and I just want to show you what the leads on this chip represent. There's a little dot right here. That's pin number 1. These 3 pins are source pins. This is the gate pin, and the 4 on the other side are drain pins. And on this particular IC, the source gets connected to the plus, and the drain gets connected to the light. But I just want to show you, these 3 pins are all the same. So there's a continuity you can hear, and no continuity with the gate. And on the other side, all 4 of these are the same. So you'll see this guy next wired into the light. The 9435 MOSFET is now soldered in place. And I'm showing this circuit diagram. Actually, it's not a circuit diagram. It's a diagram of the printed circuit board, which indicates where the devices are located and the traces that go from and to the various points of that printed circuit board. So in this particular case, the 9435 is right here, and the gate is connected to this 10K resistor right here. But take a look at what the pinout is for a 9435 MOSFET. And what it is the gate is down here. The source pins, 1, 2, and 3, are here, and the drain pins are up here. This dot on any of these devices, I think it's without exception, shows where pin 1 is. So this is a simplified diagram of this MOSFET. So here at the source is pins 1, 2, and 3. The load is up here at 5, 6, 7, and 8, and pin 4 is the gate. And the reason I'm showing this is to show you that this gate is not connected to the N or the P channel here at all. This device turns on and off with voltage only. So there's no leakage of current through here, and that makes this device very efficient. So getting back to this, I attached a wire to this gate and bent it over to run it up here to connect to this point. And in the process of doing all that stuff, I ended up breaking off the gate pin. I got so disgusted with myself that I put things down and stopped for the day. Overnight, it came to me that if I took this MOSFET and flipped it over, the gate would be over here, the source pins would be on the right side, and the drain would be on top, which is exactly where I wanted them. So I did that, and I started to solder things up just to see how it would turn out, not thinking that I was going to be able to do anything with that broken gate. While I was doing that, I took this resistor off and relocated it down here. And in the process of doing that, I ruined this 10K resistor. And I'll show you what I mean by ruin it. When I was soldering it, I suppose I put too much heat on the component and ended up removing one of the solder tabs. So you can see this device down there, and on the upper right, the solder tab is there. On the lower left, it's gone. So I couldn't use this little resistor. Now, just for your information, the numbers on the resistor are 103. What that means is 10 followed by 3 zeros, which means 10,000 ohms. If it was a 102, it would be 1,000 ohms, 10 followed by 2 zeros. So that's how these resistors are labeled. So I had to find a replacement for that, and I found this this circuit board, and I found a pretty small 10,000 ohm resistor. Actually, there's another couple of those right here. So this board has got a lot of stuff on it. A couple of switches, an IC right there, a couple of diodes. Very useful for getting components that you might need in a project that you're interested in building. So what I did was I soldered that resistor, one end of it right here, and I took a very fine wire and touched it here with some solder, and soldered the other end up here to the other end of that resistor, and it works. So I'm going to show you that. So here's the new resistor soldered in to that part of the controlling IC, and here's my flipped over MOSFET, and I'll there's that wire. It's very, very thin, but since it doesn't carry any current, it's just a voltage. I think that this will do just fine, and you can see that it works. The only thing left to do is put it all back in the case and have it ready to use the next time I do a project that requires one of these. If you've got anything out of this video, like and subscribe. I have videos about making lithium-ion battery packs on my channel. They're very worthwhile, and you can save substantial money if you make your own battery packs. I get my batteries from Battery Hookup. Just go to batteryhookup.com. My name is Marty Plecki, P-L-E-C-K-I. Thanks so much for watching. Have a great day. There's that resistor right right there, just to give you an idea of the size that I had to work with.